Hi there, geometry students. It's Mr. Pout. We're going to work through our section 4-5 today. So, chapter 4, section 5, continuing the chapter about congruent triangles. And today, your goal that you can write down is dealing with, right here, it's dealing with isosceles and equilateral triangles. So, we're going to use and apply different properties of isosceles triangles and different properties of equilateral triangles, and how we can fit that into the overall theme of congruent triangles for this chapter. All right, so make sure you have that written down in your goal sheet, please. As you do that, this gentleman over to the left, his name is Warren Moon. You may have heard of him if you're a sports fan. He played for the Houston Oilers, which is no longer a team. I believe they ended up becoming the Houston Texans, but I think there was another team in between there. Um, but anyway, his birthday is coming up. I think it's on the 18th, so depending on which day you're watching this, November 18th, I think is his birthday. Anyway, here we go. Before we get going, a couple of review questions. First of all, what is an isosceles triangle? So hopefully you remember an isosceles triangle has two congruent sides. So a picture could be, something like this. That almost looks equilateral, so I'm going to erase that. And make like, and these two sides are congruent. Alright, so it just has to have two congruent sides. Now what is an equilateral triangle? Well, that's when you have all three sides congruent. So that's where you can draw one like this, one like that. Close enough. All three sides are congruent in a equilateral triangle. The third question is an equilateral triangle an isosceles triangle? And the last one, and then is an isosceles triangle an equilateral triangle? Well, to that first question, you could say technically yes, because an isosceles triangle just has to have two sides congruent. Unless you can find a definition where it says only two sides congruent, then I'll have to look at that. It should be an equilateral triangle is considered isosceles because it has two congruent sides, but an isosceles triangle would not be considered an equilateral because an isosceles triangle does not have all three sides congruent like an equilateral triangle has to. Alright, so just to get a base as to where we're going, here's a couple terms. I know they're not definitions here, but um, if you're talking about an isosceles, again, this is an isosceles triangle right here. So the base angles of an isosceles triangle are the ones that are opposite of the two legs. So again, and the two legs are the ones that are congruent. So if we're looking at an isosceles triangle, we call the legs the congruent sides, or the two congruent sides, and the base would be the non-congruent side. All right, and the base angles then are the two angles that touch the base, and then the one other angle would be called the vertex angle, and that makes up the parts of an isosceles triangle. All right, let's do some stuff with isosceles triangles. I'll give you one at a time. The first one is the isosceles triangle theorem. So that theorem, which you should definitely add to your theorem sheet, the isosceles triangle theorem, theorem 4.3, says if two sides of a triangle are congruent, so that's our if, our hypothesis, two sides of a triangle are congruent, and here we have sides AC is congruent to BC, then the angles opposite those sides are congruent, meaning the base angles are congruent. So if AC is congruent to BC, so those segments, then angle A is congruent to angle B. And that'll always be true. If you have an isosceles triangle, the two sides that are opposite of those congruents, or the two angles opposite of the congruent sides, are also congruent. That's the isosceles triangle theorem. Then we have the converse of the isosceles triangle theorem. So let's just flip it around. Let's just switch the order. If we have two angles of a triangle being congruent, in this case we have angle A and B, then the sides opposite of those angles are congruent. So if we have two angles congruent in a triangle, that makes it an isosceles triangle. Then the opposite sides, excuse me, so the sides opposite those angles are congruent as well. So in this example, we'd have, if angle A is congruent to angle B, then segment AC is congruent to segment BC. All right, let's use those two theorems here. So, first of all, whoops. Find the value of x. So look at our triangles. We have two sides congruent. This side is congruent to this side, meaning their opposite angles are congruent. So this angle would have to be congruent to this angle. That's from the first theorem we said. If we have two sides congruent, then their opposite angles are congruent. Meaning that this bottom angle here would have to be 62 degrees as well. So to find x, we'd have to, well, remember all triangles, the angles add up to 180 degrees. So 62 plus 62 plus x would equal 180 degrees. When we subtract that, 124, oops, 124, x will be equal to 56. So that angle is 56 degrees, or x is 56. All right. Now let's use the converse. If we have two angles congruent, then their two opposite sides are congruent, so we know that 10 has to be equal to 2x minus 5. And if you solve that, it's some two-step equation here. I don't know why I added 6 to both sides. I meant to add 5. So we have 2x left over here, 15. Oops. 15 over here. And when you divide both sides by 2, you get x equal to 7.5. All right. So that's just a basic use of both the isosceles triangle theorem and the converse. Now let's look at a couple other examples to see how many we can get through here. It says an isosceles triangle DEF. I'm going to label it. D is the vertex angle, so DEF. Remember, the vertex angle is the angle that's not congruent. So remember, so then that would make that F and angles F and E are congruent. But if we have the measure of angle F is 2x, or sorry, that's 3x plus 22, and the measure of angle E is 2x plus 40. So let's find the measure of each angle of the triangle. So let's just first solve for x. So let's set those two equal to each other, since those two have to be congruent if they're the base angles. So 3x plus 22 equals 2x plus 40. Subtract 2x from both sides. Oh, we just have x alone. Plus 22 equals 40. Minus 22 from both sides. You're left with x equals 18. That does not answer your question yet, because it says find the measure of each angle. So if we plug in, so the measure of angle F, the measure of angle E, we should be able to find both of them out using x, and then D will be whatever's left. So the measure of angle F, if I plug in for x, so this would be 3 times 18 plus 22. 3 times 18 would be 36, 54? 54 plus 22 would be 76. If I plug in for this one, 2 times 18 plus 40, That would be 36 plus 40, which would be 76. That means that those two are correct. Those are both equal. And that makes up a total of 152 degrees. So this would be 180 minus 152, which equals 28. So it would be 28 degrees. And that would be number 1. I'm going to have you do number 2 on your own. We'll come back to number 2, I think, as a class next time. And we're going to go on to a new term here. So this new term, it says a blank is a theorem that can be proved easily using another theorem. And that is called a corollary. So the things that we'll see a lot of are theorems, postulates, and corollaries now. So it says since it is a theorem, you can use it as reason in a proof. So it's just like a theorem, only it's considered a corollary because it comes directly from another theorem. Now, before we get to a couple corollaries, here's one more theorem for this section. It says if a line bisects the vertex angle of an isosceles triangle, then the line is also the perpendicular bisector of the base. So if you have an isosceles triangle, which would also include an equilateral triangle, um, it says if AC is congruent to BC, that means it's isosceles, and angle ACD is congruent to angle BCD, okay, so it's really isosceles, then segment AD is congruent to segment BD. So we can prove that it's a perpendicular bisector of the base. It's also the um, oh yep. So actually I labeled that wrong over here. I wasn't talking about these two angles. I was talking about the one that was formed by the perpendicular bisector. These two angles up there. I mean those two angles would be congruent as well. But then we have that the two bases formed, those two would be congruent because it's a perpendicular bisector. So that one will come in handy. Now I have two corollaries, each coming from two of the theorems that we've talked about. The first one, corollary to theorem 4.3, and that would be to the isosceles triangle theorem. If a triangle is an equilateral triangle, then it is equiangular. So just like in the isosceles triangle theorem, which I'll back up right here, where it says if we have two sides congruent, then their opposite sides are congruent. Same thing is true of an equilateral triangle. All the sides that are congruent, which they're all congruent, means that the opposite angles are also all congruent. So if we have look at the picture, if segment XY is congruent to segment YZ, which is congruent to segment ZX, then we have that angle X is congruent to angle Y is congruent to angle Z. So equilateral triangles are also equiangular, meaning all the angles are also congruent. Then theorem 4, a corollary to theorem 4.4, which is the converse of the isosceles triangle theorem, says that if a triangle is equiangular, then the triangle is equilateral. So we know that then the sides are congruent, and that's over here as well. If the angles are all congruent, then all the sides are congruent. A couple useful theorems there. Actually, they're called corollaries, but we said those are theorems that are proved from a different theorem. Just take one note though. Each angle of an equilateral triangle measures what? Well, that measures 60 degrees because they have to add up to 180, and if they're all the same, then they're 60 degrees. They are equiangular. I'd like to go through one example, and then we'll go through the proof together as a class. So, number one, it says triangle EFG is equilateral. So we know that segment GE is congruent to this one, which is congruent to this one. And segment EH bisects angle E, meaning that these two angles are congruent. Angles 1 and 2 are congruent. Find the measure of angle 1. Well, if it's equilateral, then each of the angles measure 60 degrees. So the measure of angle E equals 60 degrees. And if we're bisecting that cuts it in half. So the measure of angle 1 and the measure of angle 2 have to be congruent, and they both have to be 30 degrees. Now it says find x. Well, another from theorem 4.5, we know that this bisects it's a perpendicular bisector, meaning these two are perpendicular, they're right angles. So if we know that 15x is in there for that right angle, that's equal to 90 degrees. And we can divide both sides by 15 to get x equal to 6. So that's just using theorem 4.5. Alright, we've got one proof that I'm going to have you try to do on your own. Try to do as much of this on your own as you can. You're given that segment HT and HA are congruent. Now think about it. That forms a triangle if two sides are congruent. What type of a triangle is that? We want to try and prove that angle 1 is congruent to angle 3. So it should only be a few step proof here. Try that on your own, and we'll talk about it next time we see you. Alright, talk to you later.